A molecule is always vibrating. In the molecule, each biatom system vibrates with a specific frequency. These frequencies provide the molecular fingerprint, which can be determined by vibrational spectroscopy. When a molecule is illuminated by a beam of monochromatic light, some of the scattered light, due to molecular vibrations, have different frequency than that of the incident light. This is called Raman effect, which was first described by the Indian physicist C.V. Raman in 1928. A more detailed explanation of the Raman effect is as follows. When a molecule is illuminated by light, it gains energy and leaves its initial equilibrium state to a higher energy state called a virtual state. When this molecule falls back, it either relaxes to its initial state or to a state which is higher or lower than that. The light which is scattered from these states represents the Raman scattering. Hence, by measuring the scattered light frequency using Raman spectroscopy, the molecular composition of each biatomic component can be characterized. Let us see how a Raman spectrum looks like for a molecule such as limonene. However, limonene, as most of the molecules in nature, exists in two enantiomers, mirror image of each other. One smells of citrus fruit, the other of turpentine. In the late 60s and beginning of 70s, it has been found that when the two molecules are exposed to linearly polarized light, the Raman spectra appear identical. But when circularly polarized light is used, the two molecules appear opposite to each other. This takes place due to the fact that a chiral molecule scatters a circularly polarized light differently depending on its chirality. Therefore, Raman spectroscopy allows for discrimination between molecular enantiomers or chirality, and this tool is called Raman optical activity, or ROA. In the mid-70s, it has been shown that the sensitivity of Raman spectroscopy can be enhanced when a molecule is found in the vicinity of the Earth's surface of a nanoparticle, such as silver or gold. Here, a field called plasmon takes place, which enhances the scattering cross-section under certain circumstances by thousands of million times. Accordingly, this allows for detection of a molecule in very low concentrations, even down to the single molecule level. Raman spectroscopy was since then recognized as a more powerful tool and called surface-enhanced Raman spectroscopy, or SERS. Making use of the surface-enhanced effect in Raman optical activity, a novel tool in Raman spectroscopy is now called SER-ROA. The sensitivity of ROA in determining chirality, secondary, and tertiary structures of molecules was limited to samples of higher concentrations. With SER-ROA, this obstacle is no longer a problem, as studies of molecular compounds at even below micromolar concentrations are possible.